All right, so this is section 3.5, part 2. And we're going to start this part of this video with production runs, which is about the same thing as the lot size, but when we're dealing with manufacturing. So like for example, if a book publisher can estimate the yearly demand for a book, he or she may print the yearly total all at once, which would incur high storage cost, or he or she may print them in smaller runs throughout the year, which incurs setup costs for each run. Okay, so here the setup cost for each printing run would play the role of the reorder cost for a store. All right, so this would work for any type of manufacturing, anytime you're building a product. All right, so looking at example 2, it says a publisher estimates the annual demand for a book to be 4,000 copies. Each book costs $8 to print, and setup costs are $1,000 for each printing. If the storage costs are $2 per book per year, we need to find how many books should be printed per run and how many printings will be needed if costs are to be minimized. So in this case, in this problem, our X is going to be the number of books per run. Okay, so each printing of the book. So there's a couple things that we need to find. We need to find storage cost and production cost. Okay, before we can find the total cost. So our storage cost works the same way as it did for the lot size. Here we have that average cost times how much it costs per each book. So here the average cost still is that X over 2. And we're told in the third sentence that the storage costs are $2 per book per year. So X over 2 times 2, which gives us the nice pretty equation of just X. So then we also need to look at production cost. And to come up with production cost, we need to know how much is it going to cost each run or each printing. So I'm going to slide down here real quick. For those production costs, let me zoom this in just a little bit. There we go. So for production cost, we have the cost per run, which gives us $8 per book. If you look in sentence 2, it costs $8 to print and $1,000 for the setup. All right, so 8x plus 1,000. And then we need to figure out the total production cost. So the production cost is equal to how much it costs per run times how many we're putting in each run, which is going to be that 4,000 total that we want to print divided by how many are in each run. All right, from there, we can come up with our total cost function. So total cost is going to be your storage cost plus your production cost. So in this case, that cost function is going to be X plus the 8X plus 1,000 times 4,000 over X. All right. If you simplify that equation, we end up with X plus 32,000 plus 4,000,000 x to the negative 1. All right. So in this case, we know we're trying to minimize cost, so we got to take the derivative. C prime of x would give us 1 plus, or not plus, sorry, minus 8 million x to the negative 2. If we solve that for by setting it equal to 0 and solving for x, we end up with x equal to 2,000. All right, the second derivative test would show that we've got c double prime of x. If you take that derivative, it's always positive, because the negative 2 times the negative 8 million would give us negative 16 million, x to the negative 3, which is always going to be positive. So we know that we've minimized this function. So to minimize cost, we need 2,000 books per run. And then we should run 2 printings. Is if you do 4,000 divided by 2,000, that gives us 2, so 2 different printings to minimize our cost. All right, let's keep going. The next thing that we're going to talk about, my thing will move, there we go, is sustainable yield. So the next application involves industries such as fishing, in which a naturally occurring animal population is harvested. Harvesting some of the population means more food and other resources for the remaining population, so that it will expand and replace the harvested portion. But if you take too large of a harvest, it's going to kill off the animal population. So what you need to do is find what we call the maximum sustainable yield. And this is the largest amount that may be harvested year after year and still have the population return to its previous level the following year. So this maximum sustainable yield would be used to figure out how many fish you could pull out while still maintaining the growth that you need. All right, so for some animals, one can determine a reproduction function, that f of p, which gives the expected population a year from now if the present population is p. All right, so our reproduction function, f of p, gives the population a year from now given your current population. And suppose that we have that reproduction function f and a current population of size p. Therefore, this is going to grow to size f of p next year. So the amount of growth that's taken place is f of p minus p. Harvesting this amount removes only the growth. So the returning, which returns the population back to its former size p. Okay? So if we have this formula, this setup, what that gives us is what we call sustainable yield. So the population will then repeat this growth, and taking the same harvest, f of p minus p, will cause this situation to repeat itself year after year. So the quantity f of p minus p is called sustainable yield. So we're only taking off the growth, we're only taking off the change for each year, and you're keeping the population, the current population, stable year to year. So we want that population size p that maximizes the sustainable yield y of p. And to maximize the sustainable yield y of p, we set its derivative equal to 0. So y of p would be equal to f of p minus 1. Okay, because p is our x value here. So the derivative of p is just 1. Setting that equal to 0 gives us f prime of p equal to 1. So, for a given reproduction function, f of p, we find that the maximum sustainable yield for solving this equation, provided that the second derivative test gives y double p less than 0, gives us the maximum sustainable yield. So we're on slide 19. For reproduction function, the maximum sustainable yield, f of p, the population p that results in the maximum sustainable yield, is the function, the solution f prime of p equal to 1. All right, so once we calculate the population p that gives the maximum sustainable yield, we wait until the population reaches this size and then harvest, and year after year, an amount y of p. All right, so the reproduction function for the American lobster in an East Coast fishing area is f of p equal to negative 0.02 p squared plus 2p, where p and f of p are in the thousands. Find the population p that gives the maximum sustainable yield and find the size of that yield. All right, so again, we know that f prime of p needs to equal 1. So I want you to work this out and solve it and come back and check. All right, so if you find your f of p is negative 0.02 p squared plus 2p, if you find that derivative and set it equal to 1, and then solve that equation, you end up with p equal to 25. Okay, so I'm right here, this arrow, p equal to 25. Taking the second derivative gives us a negative number, so we know that we have a maximum. So that means 25,000 lobsters. If we get to a population of 25,000 lobsters and then yield, we can plug the f of p minus p into the maximum yield or maximum sustainable yield equation. If we plug that all in, y of 25 would give us 12.5, which means once the population hits 25,000 lobsters, we can pull out, we get a yield of 12,500 lobsters, which would take it back to where we started and start the process over again. If you have any questions, let me know. That's the end of 3.5.